Software Engineering Radio, episode 122, interview with Janos Sztipanovits.
This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for support. So Janos, please introduce yourself to our listeners.
My name is Janos Sztipanovits. I am professor at Vanderbilt University. Vanderbilt is in Nashville, Tennessee. I'm director of the Institute of Software Integrated Systems, ISIS. ISIS is a university-affiliated research organization. We have about 35 full-time researchers, engineers, 8 affiliated faculty, and roughly 50 graduate students. So it's the size of ISIS is relatively big relative to the usual academic measures. Mm-hmm. My research interest, is in the design and implementation of systems that are both computational and physical. So they include computational components and physical components. Okay. Related to this, on the computational part, I started working in the over 20 years ago on model-based design. Our take on model-based design is called model integrated computing, or MIC. Distributed real-time embedded systems is a particular kind of computational target for model integrated computing. But you know that you can do model-based design for just about anything.
Yes.
So that's one of the target platforms, the distributed real-time embedded system platforms.
Mm-hmm. Yep.
But we are very heavily involved in the system side of the overall landscape, control, digital signal processing, adaptive systems, and I did quite a bit of work in those areas as well.
Mm-hmm. So in the material I used for preparing this interview, you talk about cyber physical systems. Sounds to me a little bit like the new buzzword. Can you outline what those systems are all about?
Indeed, it sounds like a new buzzword, particularly if you compare it with the usual embedded systems or network embedded systems area. But let me just make a pitch for this new terminology. Mm-hmm. So, as you know, in many ways, one of the greatest ongoing transformation in technology is that networking, computing is more and more penetrating quite deeply into physical systems. In fact, we use these systems as a universal system integrator these days. Yeah. That kind of deep penetration of networking and computing in large scale and even small scale engineered systems, what we build, is a major revolution. It started 20, 15 years ago, and that's gradually transforms whole industries. Mm-hmm. It goes so far that these days, if you look engineered products in major areas like avionics and others, the computational networking component quite a bit exceeds 50% as value added. Mm-hmm. Now, the traditional embedded systems view of this area is let's see what the physicality in the environment does to computing, specifically how we form requirements, how we build software for these systems, what kind of network properties we build. But again, the focus is what the physicality of the environment does to computing. But there is a very important other side of the story. What the embedded computing and networking does to the engineered systems. Right. Yeah. Ultimately, that's what drives the whole process. Mm-hmm. And cyber physical systems try to emphasize that what we are looking for a system category which is so tightly integrated that you cannot sort it out. What is the computational part? What is the physical part? Because both of these sides inherently needed to implement the new properties. So what we really want to look in the cyber-physical systems, what are these new properties? What are the new qualities that the integration of physical and computational objects can bring in these systems? So that's what we mean by cyber-physical systems.
Okay, so before we look at some of those properties and challenges, can you give us a couple of maybe a little bit more detailed examples of where these kinds of systems show up? You already mentioned, I guess, avionics and probably defense. So can you give us an example so people can imagine where this kind of stuff shows up or is used?
All of those industries, what you would traditionally call systems industries, so aerospace, of course, all aspects of aerospace. If you look at avionics systems, flight control systems, or just you look modern airplanes, they are clear example for cyber-physical systems. The other major industries, of course, automotive industry. Yes. If you look the modern cars, the electronic content is tremendous, and the new features, what embedded electronic does to the cars, to the dynamics, the drivability, the energy efficiency of the cars is huge. But there are many others: industrial automation, telecom, health and medical equipment. So it's just about the most pervasive transformation that really across all major engineered systems.
Mm-hmm. You talk about a specific design flow that is relevant for cyber-physical systems. Can you give us some details here?
What I would really advocate here is that the design flows, what you use for building cyber-physical systems, are inherently heterogeneous. Typically, they cross or they include three major disciplines. Of course, software and computing is one general area. Yeah. But it also includes control and systems engineering. Mm-hmm. Somehow the design flows are built as the combination of these different kind of engineering disciplines. Now, the other part of it is that design flows are usually built such that you have to highly customize them to the needs of the actual domain. Yeah. Obviously, design flow for engine control or drivetrain control in cars is different than design flows for process automation, because the nature of the system is different. Your attention, the optimization requirements are highly different. So if there's one thing which is common in all of these design flows, that they have to be highly flexible. Mm-hmm. You have to be able to define in the design flow specific abstraction layers. These abstraction layers give a way to express your design ideas, implementation ideas, where the other layers. And you compose the overall flow along the usual step refinement mapping across these different abstraction layers.
And so what you're doing here, and what's also probably going to be part of your OOPSLA keynote, is that you use domain-specific languages for modeling or designing the systems on these different levels, right?
Yes. What actually is a very interesting phenomenon that in these three disciplines, software, control, and systems, but I may also need to append here security engineering, which is becoming a very important issue. Yep. The different domains or subdomains bring their own engineering disciplines and methods with them. Mm-hmm. Now, control engineering and systems engineering has been traditionally model-based. That's how they train people. That's how they think. That's how their tools look like.
It's interesting to if you go to get together with control folks and they talk about models, and then you take some software person and also use the term model, those people mean completely different things and often have a hard time actually understanding each other. My girlfriend works in control automation, and if we talk about model-driven or model-based, we hardly find a common understanding.
But in the same time, though the modeling languages can be different,
yes,
what's
exactly.
really emerging that because modeling really gained tremendous weight in software as well,
yep.
That gives us an opportunity to make a new synthesis. And
yep.
Basically, in my Uppsala keynote, I really would like to focus on this new synthesis, that
yep.
The opportunity for convergence that all of these create. And indeed, what I feel is that domain-specific languages and just the whole agenda of being able to look from a higher level, what are these languages? How can we define them? How can we compose them? Gives us the opportunity for major convergence across these areas.
Yes,
that convergence is not done yet, but certainly we understand better, more and more how it could be done.
Right. Yeah, I agree. As you know, I also work in the model-driven area, and I also always talk about that in my trainings, that you can also model hardware and stuff with modeling languages, and on model level, software and hardware are the same. They're part of the same model or set of models, and as you say, that gives you a very new way of seeing all those things under the same meta concept or something.
Yes. That's actually, in our experience, is one of the concepts that are hard to get through for other disciplines.
Mm-hmm.
The software folks are very easily understand these different abstraction layers, and just the fact that the abstraction itself can be the objective of design. You know, if you look at the disciplines like traditional electrical engineering,
mm-hmm.
The education is built up in those areas such that students are receiving as part of their education very precisely formed abstraction layers down to the notations.
Yep.
And therefore, it's deeply ingrained that how I need to represent and deal with let's see, linear system dynamics or digital circuits.
Right.
This is taught in one package. It never comes up that why would I want to change the notation? Why would I want to design new abstractions for describing a new domain, which is part of the whole software and computing mindset.
Yep.
So that's really the interesting aspect of this whole synergy which is evolving.
An interesting tangent here is maybe, have you heard about Janet Wing's computational thinking?
Yes.
I think that's a very interesting idea or realization or whatever, to teach non-computer scientists, abstraction, state-based behavior, and these kinds of things. Although they don't do software, it's still relevant for building systems.
Yes, that's indeed a tremendous opportunity, and frankly, that convergence, which is based on the cross-fertilization of these areas, is a huge promise.
Yeah.
So I think that type of computational thinking, where one element of it is that you teach in other disciplines how you formulate, adjust, modify your abstraction, is a very important idea.
Yeah. Okay, so why don't you outline some of the main challenges in building those cyber-physical systems?
One of the most important things, of course, in all engineering systems is composition.
Yeah.
Composition is our bread and butter to manage complexity. You know that composition has two aspects of it. One is compositionality, which means that the properties can be computed from the local system-level properties can be computed from the component, and composability, which means that the components will not change their properties when you put them into system.
Yep.
But of course, this is a very hard thing to do if you are building large interconnected systems that are inherently heterogeneous.
Yeah.
What we usually tend to do, that in order to manage complexity, let's say in cyber physical system, how would you do that? Well, this is our tradition. Usually we build software. So there is a software discipline which will design the software architecture.
Right.
Then we define the control. Then we define the systems engineering part as separate disciplines, as if the other would not exist.
Yeah.
But the other exists, of course, because we are designing exactly the same systems. There are a whole lot of interactions, and if you stick strictly with this separation of concern idea, these interactions are not modeled. You are sitting happily in your modeling world of control without considering what the implementation, the computational components implementation will do to you of your system dynamics. So resolving these issues, how can I reconstruct or develop theories for composition in heterogeneous systems is certainly one of the major challenge.
Mm-hmm.
Now, another major area what really is just inherently part of all model-based design is that we use tools.
Right.
The whole model-based design is driven by or opens up the opportunity to do tool-based approaches.
Yes.
So we engineer the system, we specify them, we refine the models, we extend them, we transform them. And now if you look at the design automation market and where are we in design automation in general for this kind of system category, what you see is that, of course, wherever you have a massive market which provides stability and longevity for developing high-value tools, then those tools are created and exist. Of course, VLSI design is a canonical example for this, where these high-value design automation tool chains have been created. The situation is much, much worse and much messier in CPS, cyber physical system. Why? Because there are so many of them. We need so many different kind of flavors. Again, as we were talking about it earlier, what you need design flows and related tool chains in automotive might be quite a bit different from the tool chains what you need for embedded sensor networks or for avionics systems.
Do you think that SysML is a viable standard to create this bigger market so that good tools can emerge, or is SysML has the same problem as UML in that it is too generic?
Yes, so that's the problem. That if you want to buy out yourself from the need for flexibly creating and customizing design flows, modeling concepts, and create these monolithic large languages, then perhaps you can get a hope that you recreate based on large standards like the SysML, the environment for these complicated design automation tools with. But I strongly believe that there will be always a variety. The areas across the different subdomains are, the difference is so big that it will not allow to select one or the other standard over as a dominant thing. So it's not like computer languages. It's the differences are essential. So there is no other way than just to understand how to resolve the dichotomy. How can I build in a very flexible way, highly customized design automation tools, but in the same time not lose reusability.
Right.
So that's basically the most exciting technical challenge for this area.
Right, I agree. And in software, it's kind of the same thing. I mean, many people say that UML is good enough for everything, but of course, the whole DSL advocates who just do software, like the meta-edit folks or also myself, they strongly believe and know from experience that more specific languages are better. So even in the software world only, I think this problem exists.
Yes. Yes, indeed. And it's particularly essential in the in this cyber physical system world, where heterogeneity is really going very deep and very far.
Two other things you talk about is certification and security. I guess the certification aspect is probably especially relevant in avionics and other like high-risk environments, right?
Yes. Certification of these cyber physical systems is one of the huge challenge that the systems companies are facing, and as you know, that much of the certification-related standards are really highly process-based. There is no such things that compositional certification. Usually, if you make any change in some aspect of the system, simply because of the lack of compositionality in the overall system design, and because of the unmodeled potential interactions across, you have to recertify the whole system. And that needs to be resolved. Certification, of course, is a major problem for the avionics folks, the aerospace industry. I'm sure that everyone heard these tremendous cost numbers. How much does it cost to certify a large new airplane? It's billions and billions of dollars. And really, if that issue is not solved, sooner or later, just the requirement and the cost of certification will be a huge pushback. To build these systems.
It's even in like general aviation, very simple systems, Diamond, who have a hard time certifying their new diesel engines. There isn't much cyber physical systems involved. It's just certifying hardware. I guess if you do cyber and software stuff, it's way more complicated even.
Yes. And of course, hand in hand with this come the whole area of system integration. The system integration these days is that you build all of the components, hoping that at the end of the day we just plug them together easily, because plug and pay and create the complex system and everything works. But again, the problem is the many unmodeled interactions, and the result of this that. This whole one-shot system integration, which is focusing on delivering components in the system integration labs, is just not scaling. It's uncontrollable. It's very hard to predict what will be the cost. And usually the solution is that people are just doing the system integration by testing and testing and testing until the money is running out. And that, of course, costs and ruins quality and results in tremendously expensive recalls in the automotive industry and so forth. So that whole issue has to be reconstructed. And of course, there are new emerging, very nice techniques that are model-based, that try to systematically approach this, try to do incremental. So you pursue an incremental concept of system integration, that you always have some version of the system which is operating, where you can shift in and out parts of the system from only modeled to real hardware or real software in the loop elements. So there is a huge transformation also what I see in the whole system integration area.
So in your Uppsala keynote, you're probably going to outline those challenges and maybe some solutions, right?
Yes, I really plan to talk about these challenges, show examples how this fundamental transformation is going on, and again, what I'm really captured by, that I feel that very interesting convergence which is emerging across these isolated disciplines, and that has very deep impacts, not only how we do the practice, but how we teach engineering. and as an academic who is involved in curriculum and creating courses and so forth, that's also a very important aspect of the overall story.
Okay, then Janos, thank you very much for being on the Oops Lab podcast, and I guess you did motivate people to actually come to your keynote, which is one of the points of this podcast.
Thank you very much.
Thank you. Thanks for downloading and listening to Software Engineering Radio. Software Engineering Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@se-radio.net, or if it is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under a Creative Commons 2.5 license. Please see the website for details. Thanks to Charlie Crow and the PodSafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.